Hi, my name is Jonathan Meerholz.
And my name is Mihir Vanmali, and today we present to you
An investigation of a fast monocular geometric positional tracking technique
with specific applications in traffic monitoring.
That's quite a mouthful. Let's break it down. When you think of visual object tracking, the first thing that comes to mind are the recent developments in self-driving vehicles.
This problem is typically solved using an onboard camera paired with intensive machine learning algorithms.
The onboard approach has a major disadvantage. The tracking ability of these systems are limited to the driver's point of view, as shown in this scenario. Notice the red car.
Whereas from the static peripheral perspective, we can gain increased perception, such as being able to see around corners.
By fixing the environment, we eliminate the number of unknown variables that an onboard system has to solve for.
This allows for high-performance specialized analytic solution as opposed to a more generalized numerical solution.
Thus, we present an overview of our static peripheral system.
We begin with the known background image and input video frames.
We then apply downsampling techniques which reduce the size of the images, thus reducing the number of pixel computations.
The simplification process is extended to averaging the RGB channels to a single grayscale image.
The foreground objects are isolated by means of background subtraction.
The image is then binarized by means of a threshold value, classifying pixels as either a foreground pixel or a background pixel.
The raw foreground pixels are filtered by various morphological operations, removing noise.
These pixels are then clustered into individual blobs described by a bounding box.
With the objects tracked in the current frame, the next step is to determine the 3D positional description of the detected objects.
To understand how the global 3D position is obtained from a single 2D image, it is useful to overview how a 3D object becomes a 2D picture.
Here, we take the perspective of the camera, which is represented as a pinhole camera model.
As we move around, it is apparent that a light ray will travel from the car and through the aperture to produce an inverted image on the focal plane.
By performing the inverse operation, we can move from this inverted 2D image and determine the object's 3D location, given that the description of the ground plane is known.
In order to validate our positional tracking, we developed a 3D traffic simulation where the exact positional information of the target objects are known.
This is advantageous as the exact positional data is not easily determined through real footage.
To benchmark the performance of our system, it was important to find an existing, credible comparison.
Thus, it was found that MATLAB's automated driving toolbox provided a similar monocular tracking technique.
Here we compare the tracking results from both our system and MATLAB's at their respective frame rates.
Notice that the implemented technique outperforms MATLAB's toolbox in both frame rate and tracking consistency.
During the development of the presented solution, it was observed that many existing monocular location tracking techniques require that objects are on a single flat plane.
This limitation was explored, and a solution was developed such that the environment can be modeled by multiple planes, thus allowing for positional tracking on multiple surfaces.
To the best of our knowledge, this is the first implementation of such a technique.
Thank you.